Welcome to The Explainer. So today we're diving straight into the incredible, completely invisible infrastructure that literally powers our modern world. I'm honestly so excited to guide you through this because we're talking about fiber optics. It's this mind-blowing technology that's just hidden right beneath our feet and at the absolute bottom of our oceans, yet it completely dictates the pace of our daily lives. We're going to trace the journey of light today, from how it forms the backbone of global telecommunications, all the way to how it's being used right now to perform actual medical miracles inside the human body.
To really get a grip on this, I want you to think about something for a second. How does a phone call cross the entire ocean in literally milliseconds? Just think about the sheer, mind-bending scale of global communication. You speak into your phone, and before you even take your very next breath, someone on the exact opposite side of the planet hears your voice with crystal clarity. To understand how that magic actually happens, well, we have to look at the fundamental speed limit of the universe.
And that ultimate speed limit is exactly 300,000 kilometers per second. That's the speed of light in a vacuum, like outer space. Harnessing this ultimate speed is the real secret to everything we'll cover today. Rather than using slow, clunky electricity or sound to carry our data, humanity figured out how to use the fastest thing in existence.
Let's put that into perspective, right? Let's look at a 16,000-kilometer journey. That's the distance of a typical phone call traveling all the way from Sydney, Australia to New York. By using light, the minimum delay between when one caller speaks and the other hears them is a mere 80 milliseconds. 80! That is barely a fraction of a blink of an eye.
Now, what's really fascinating here is that using light to communicate, it's not actually a new idea. Humanity has been experimenting with this for centuries. We're talking ancient Greeks and Romans using polished mirrors to flash sunlight and send messages. Then you skip ahead to Alexander Graham Bell in 1880, all the way through the invention of the laser in the 60s, and finally those crucial low-loss silica glass fibers of the 1970s. That was the breakthrough that made our modern, long-distance digital world possible.
Okay, let's dive into this for a second, because Bell's 1880 invention, the photophone, was absolutely brilliant. Instead of wires, he used sunlight reflected off a vibrating mirror. So the mirror was attached to a microphone diaphragm, and as a person spoke, the acoustic energy of their voice actually vibrated the mirror, which changed the intensity of the light beam. That beam then traveled over to a selenium photocell that converted it right back into sound. It literally took another 80 years for the glass and electronics to catch up to how genius this concept was.
So how do we actually trap this light and shoot it around the globe today? The answer is total internal reflection. An optical fiber is made of two main layers of dielectric materials. You've got a central glass core surrounded by a cladding layer. The trick is, the core has a slightly higher refractive index than the cladding. So when our data-packed light pulse enters the fiber at just the right angle, it hits the boundary between the core and the cladding and bounces perfectly back inward. It gets completely trapped, just ping-ponging safely off the walls as it shoots down the cable.
But there are physical rules to this journey. Remember that 300,000 kilometers per second speed limit? Well, the index of refraction dictates that when light travels through a medium like glass, it actually slows down a bit. Inside a typical telecommunications fiber made of pure silica, our light pulse travels at roughly 200,000 kilometers per second. So yeah, even though it's slowed down compared to traveling through a vacuum, it remains astonishingly, unbelievably fast. Before this light even sets off on its massive journey, we have to pack it with information. We do this using digital modulation, where an electronic pulse is quite simply translated into light. The absolute simplest form is on-off keying. A light pulse switched on represents a digital 1 and off represents a 0. Millions and billions of these tiny microscopic flashes are fired into the fiber every single second. It's wild. But the journey isn't perfectly smooth. Our light pulse actually faces two main physical villains along the way: attenuation and dispersion. Attenuation is just a fancy way of saying the loss of signal intensity as the light travels through the fiber. Think of it like a flashlight beam getting dimmer and dimmer the further away it shines. Dispersion, on the other hand, is when the light pulse itself spreads out over time. That causes the signal to get all jumbled up and much harder for the receiver at the other end to understand. And this brilliantly illustrates what we mean. Imagine a beam of white light hitting a glass prism and separating into a rainbow. That separation happens because different colors, or wavelengths, of light actually travel at slightly different speeds inside the glass. Inside an optical fiber, this means the different wavelengths making up our data pulse start to separate over long distances, causing the pulse to smear out and literally overlap with the next one. Because of this, engineers actually have to fight a few different types of dispersion just to keep your internet fast. We just saw chromatic dispersion, right? That's the different wavelengths traveling at different speeds. But they also have to account for modal dispersion. That happens in wider fibers where the light can take multiple different bouncing paths, meaning the signals arrive at slightly different times. And there's even polarization mode dispersion, which happens when the horizontal and vertical states of the light wave travel at slightly different speeds because of tiny, microscopic imperfections in the glass itself.
Now, beyond the complex physics, our light pulse faces some surprisingly rugged real-world threats. Believe it or not, deep-sea sharks have actually been known to attack and bite undersea optical cables. I mean, some theories suggest they're drawn to the electromagnetic fields or maybe the chemical sheathing. And if that wasn't crazy enough, up on land, termites have been documented attacking and eating the protective plastic sheathing of fiber cables. So yeah, even our most advanced, cutting-edge tech has to battle nature.
Despite the sharks and the physics, the transition to fiber was just inevitable. Just compare them. A bulky 7.6 centimeter copper bundle weighs over 11,000 kilograms per kilometer and carries maybe 21,000 channels of traffic. Meanwhile, an optical fiber cable is just 1.2 centimeters thick, weighs a mere 90 kilograms per kilometer, and can carry around 300,000 channels. The light pulse is the undisputed heavyweight champion of data delivery, which is funny because it wins by being incredibly lightweight.
And fiber didn't just win on size and weight. Because it uses light inside an insulating glass dielectric, it has total immunity to electromagnetic interference. It is not going to pick up static from nearby power lines. It's also incredibly secure because it doesn't leak electromagnetic signals that someone could easily tap into. Plus, it's highly resistant to extreme heat. I mean, silica melts at a massive 1900 degrees Celsius. Add to that a data capacity that is theoretically infinite as our multiplexing tech gets better, and copper just didn't stand a chance.
Okay, let's pivot the narrative here. We know light connects our continents, but its journey absolutely does not end there. We are now transitioning from the massive global scale of telecom down to the microscopic, life-saving applications of fiber optics inside the human body itself. This is where it gets really sci-fi.
Because optical fibers are non-toxic, chemically inert, and can be made incredibly small, they're quite literally the perfect medical tool. First off, we have endoscopes. These use flexible fiber bundles to give doctors a direct visual inside the body without needing to make massive surgical incisions. Then we have optical coherence tomography, or OCT. Think of this sort of like an ultrasound, but instead of sound waves, it uses light. It captures high-resolution 3D images of human tissue in real time. It has completely revolutionized how we diagnose things like coronary artery disease.
And the research here is just moving incredibly fast. Standard glass fibers are great, for sure, but they're rigid. So researchers at MIT and Harvard Medical School have developed stretchy, flexible optical fibers made of hydrogel. This is a material that's almost entirely water, making it highly biocompatible. The ultimate goal? Optogenetics. They want to use these tiny elastic fibers, which can literally stretch over 7 times their original length, to safely deliver light directly into the brain to activate specific neurons and brain cells.
If you thought that was cool, scientists at the University of St. Andrews and Harvard are currently developing biodegradable optical fibers. Imagine having a delicate internal surgery. Instead of leaving permanent glass inside you, doctors could insert these temporary fibers. They use a process called photochemical tissue bonding, which combines laser light with specific dyes to essentially weld internal wounds closed, from the inside out. And once the healing is done, the fiber simply dissolves and gets safely reabsorbed by your body. No second surgery required. Incredible, right?
Which brings us to our final thought. We started with ancient Romans using mirrors, and today we have dissolving strands of light healing wounds from within, alongside invisible beams of data crisscrossing the ocean floor in milliseconds. The journey of light has absolutely transformed human existence. So I want to leave you with this. If light can do all of this today, what on earth will it connect next? Thank you so much for joining me on this Explained today. I really hope this sparks some curiosity, and as always, I encourage you to keep exploring.